Welcome to today's technical session presented by Qfnsoft. Today we're going to look at how we can use ANSYS Rocky and ANSYS OptiSLang to optimize a vertical mine ore pass. So first I will address ANSYS Rocky. So let's examine the key market trends driving DEM simulation software today. The market is experiencing strong growth due to three main drivers: vertical prototyping, process optimization, and cost reduction across industries. We are also seeing exciting advances in multi-physics coupling, enhanced computational power, and more user-friendly interfaces. This brings us to three critical challenges the market is addressing. First, predicting particle flow behavior. Particle interactions are complex, involving shape, size, material properties, and more. Accurately modeling requires accounting for all these variables. Second, multi-physics solutions. Today, applications require integrating particle simulations with structural, fluid, and electromagnetic analysis for comprehensive real-world modeling. Third, computational limitations. The challenge is simulating millions of particles accurately while maintaining reasonable simulation times and computational requirements. This demands faster, more stable solvers. These trends are creating new opportunities for more accurate and efficient simulation across industries. Now let's dive into Rocky and see how it addresses these market challenges we've discussed. So ANSYS Rocky is our advanced particle simulation solution designed to tackle the most demanding DEM simulations across industry. What makes Rocky truly exceptional is its ability to accurately and rapidly simulate complex particle dynamics through several key innovations. Rocky stands out particularly for its advanced real particle modeling and sophisticated braking capabilities. It features a powerful native multi-GPU solver that delivers outstanding performance, plus it integrates seamlessly with the entire ANSYS product suite. And importantly, it offers extensive automation and customization options. So let me highlight three key differentiators. First, advanced particle modeling. This is where Rocky really shines. Unlike traditional spherical particle assumptions, Rocky can model real particle shapes, including solids, shells, and even rigid and flexible fibers. You can define and import your own custom particle shapes to achieve true real-world representation. This means your simulations accurately reflect how your actual material behaves, not just simplified approximations. Second, speed and scalability. Rocky addresses those computational limitations we discussed earlier. By computing power through its multiple GPU solver, Rocky dramatically overcomes memory limitations and delivers substantial performance increases. We're talking about the ability to speed up particle simulation significantly and handle large-scale simulations involving millions of particles, something that was previously computationally difficult. Third, automation and customization. Rocky provides comprehensive automation and customization tools to boost productivity. This includes pre-processing script capabilities that let you create and modify Python scripts for automating repetitive tasks. There's also the SDK solver for customizing modules and PyRocky for customizing workflows through Python scripting. This level of flexibility means you can tailor Rocky to fit your specific simulation needs and workflows. These three differentiators work together to deliver a solution not just powerful but practical for real industrial applications. So let's see how ANSYS Rocky addresses each of the three market challenges we identified earlier. As I stated, Rocky is the industry-leading discrete element modeling software that quickly and accurately simulates particle flow behavior. Rocky's multi-GPU solver capabilities makes it possible to solve large-scale simulations faster, involving millions of particles of different sizes and shapes. So let me show you the direct customer benefits Rocky delivers. For the challenge of predicting particle flow behavior, ANSYS Rocky creates realistic particle shapes, spheres, non-spheres, fibers, and shells that settle and compact like actual particles. This means your simulation results are far more accurate because they reflect real-world particle behavior, not simplified assumptions. For multi-physics simulation solution, Rocky's powerful integration with other ANSYS products transform it from just a discrete element modeling tool into a comprehensive multi-physics simulation platform. You can couple particle dynamics with structural, thermal, and fluid analysis seamlessly. For limitations in time and computational resources, Rocky multi-GPU solver efficiently is a game changer. You can now run simulations with millions of particles in significantly less time without compromising accuracy. You used to take days, now you can complete it in hours. Rocky doesn't just solve challenges, it transforms how you approach particle simulation making by making complex, accurate simulations both faster and more accessible. So there are various types of equipment in the mining industry, such as mills, crushers, transfer chutes, vibrating screens, mixers, bucket conveyors, screw conveyors, trucks, excavators, and blast furnaces. So these are all just a few examples of where Rocky can be used in the mining industry. So let me quickly show you how Rocky has come and has evolved. Back in 2000, DEM was quite limited. We only could handle a few 100,000 particles, mainly spheres or simply glued spheres, and it was primarily an R&D tool. So fast forward through continuous innovation, particle shape modeling in 2011, native GPU acceleration in 2015, multi-physics integration in 2016, multi-GPU capabilities in 2017, and flexible particles in 2018. We've constantly invested in strong R&D to push the boundaries. Today, with Rocky 2025 R2, we've achieved a dramatic transformation. We can simulate hundreds of millions of particles with complex shapes, fibers, shells, and using the breakage model. It's now a full multi-physics tool that's cloud-enabled with complete ANSYS integration. This evolves from hundreds of thousands of hundreds of millions of particles represents a hundred-fold increase in capabilities. That's the power of sustained innovation. So now we'll delve quickly into what OptiSLang. So let's look at the broader market trends that are driving the need for advanced simulation platforms like ANSYS OptiSLang. Today's engineering environment is defined by three critical pressures. Experts need faster development cycles with less time to market, while simultaneously meeting increasingly strict regulation requirements. This creates a perfect storm where interoperable tools and processes become absolutely essential for efficient collaboration and data management. This leads us to three key market drivers. First, competition to deliver the best products. In engineering, there's rarely one optimal design. Engineers are constantly making trade-offs between size, performance, and cost and reliability. Traditional manual approaches simply can't explore the vast design space efficiently. This is where automation becomes critical. It enables engineers to perform comprehensive optimization studies and explore multiple designs alternative of a system. Second, the critical need for automation. Automated workflows are transforming how we work. They enable repeated simulations by setting parameters, running multiple simulations, collecting results, and generating reports, all without manual intervention. This eliminates human error and dramatically accelerates the design process. Third, enabling scalable and interoperable engineering workflows. A major challenge in CAE is enabling seamless collaboration and data flow across different tools and teams. This requires interoperable workflows, robust SPDM systems, and integrated with MBSE approaches. Critically, we need to democratize simulation access to both experts and non-experts can continuously effectively without requiring extensive coding skills. These trends are driving the need for intelligent automation and optimization platforms that can orchestrate complex engineering workflows. So let me introduce ANSYS OptiSLang and show you how it directly addresses these market needs. ANSYS OptiSLang is an automation framework specifically designed for parametric design exploration and optimization in conjunction with physics-based simulations. It's the intelligent layer that makes complex engineering workflows both automated and accessible. So OptiSLang delivers three key differentiators. First, process integration. This is where OptiSLang excels at connecting, automating, and publishing simulation workflows. Instead of manually running individual simulation, OptiSLang creates intelligent workflows that can automatically execute complex simulation sequences, manage data flow between different tools, and publish results in a standardized format. This directly addresses the need for faster development cycles we discussed. Second, design optimization. OptiSLang uses advanced algorithms for parametric variation analysis. Rather than engineers manually guessing which design parameter to change, OptiSLang intelligently explores the design space using sophisticated optimization algorithms. It can identify optimal designs, understand parametric sensitivity, and reveal unexpected design insight that manual approaches would miss entirely. First, universal connectivity. Thanks to ANSYS's open ecosystem, OptiSLang connects to all ANSYS solvers, plus over 100 third-party CAD and CAE tools. This means you can create optimization workflows that span multiple physics domains and software platforms seamlessly. Whether you're working with structural, fluid, thermal, or electromagnetic simulations, OptiSLang orchestrates them all. So let me show you the real-world impact OptiSLang delivers by automating multi-physics workflows and optimizing complex designs. OptiSLang addresses the core problem of manual, time-consuming tasks in physics solvers. It automates workflows across multiple physics domains simultaneously: CFDs, structural, electronics, and thermal, solving complex multi-physics problems that no single tool can handle alone. Here are three proven customer benefits with quantified results. First, 6 times accelerated innovation. By eliminating manual discontinuous processes, customers achieve 6 times faster innovation cycles. More projects can be completed, and integration of multiple tools enables breakthrough innovations that were possible with isolated simulation. This directly addresses that time to market pressure we discussed. Second, 45% saved engineering time. Through automation and making simulations accessible to non-simulation users, customers save nearly half their engineering time. OptiSLang's automated workflows eliminate repetitive manual tasks, allowing engineers to focus on innovation rather than routine simulation management. Third, 27% lower design cost. By systematically identifying optimal designs through intelligent optimization algorithms, customers achieve significant cost reduction. Instead of settling for adequate designs, OptiSLang finds the true optimum that balances performance, weight, materials, and manufacturing costs. These aren't theoretical benefits, these are measured results from real customers' implementation. OptiSLang transforms simulation from a manual export-only activity into an automated, enterprise-wide capability that delivers measurable business value. Now I'm going to show you a demo where I use ANSYS Rocky and OptiSLang to do a sensitivity and optimization of that vertical mine or pass. So just to give you a bit of a problem statement. So we're looking at using ANSYS Rocky to do the DEM simulation and coupling that to OptiSLang. We're then going to optimize the design of the vertical mine or passes. So we're going to focus on how we can vary the angles of the second and third section and how that impacts the ore flow, the wear, and the overall system efficiency. We're going to identify the most effective geometrical configuration. So on the Rocky side, we need to define some form of modules, which will be boundary condition statistics, so we can gather information about where the wear is going to occur and the energies that have been dissipated on those collisions. Then we're going to look at physics. I kept it simple, so we're going to use spherical particles. So we're going to need momentum or addition, such as rolling resistance, to represent more realistic particles. And materials, obviously, for this particular example, I using the defaults, but you can add whichever material you require. Then we need to define our geometry, such as our walls, which will be represent the ore pass, and then the surfaces to create things like inlets. We'll add expressions to drive the geometry that can be then updated in OptiSLang. We chose spherical particles and added rolling resistance to keep it a little bit more simple for the purpose of this study. We then define inlets and outlets. Inlets, defining the flow rate of the material entering our domain. Then with the solver side, we define the simulation duration, and then we can choose if we want to use a CPU, GPU, or multi-GPU or multi-CPU. We'll then obviously look at a little bit of post-processing, where the intensities are of the dissipation, and we can also look at dynamics, at how the flow is and how it impacts on the conveyor below. Then we're going to look at getting information about those intensities, so quantitative data rather than just visuals. So we can then add curves to get information that we want to then pass on to OptiSLang. Then on OptiSLang sides, we're going to use the solver wizard to link Rocky to the project. We can then use the sensitivity wizard to get an understanding of the design response and creating a meta model of optimal prognosis, which is what is a MOP. From that information, we can then use the optimization wizard, where we will find the best design. With OptiSLang, once we have looked at various results, we can then look at, for example, the response surfaces, which is a fitted response of the results that we got from Rocky and the inputs that was driven by OptiSLang. We can look at residuals, predicting the value versus the fitted response. So we can see if the, the optimized result falls in to what was predicted. And then a coefficient of prognosis, or COP, to access the prediction quality of the approximate model. So it will give us a idea of if the model, meta model that is being used accurately represents the simulation results that we receive from Rocky. You can then also look at the COP matrix, understand the COP of each input for a particular result. So I'm going to show how we set up the project in Rocky. So I'm going to create a new project, and then the first things I want to do is add the modules that I want to add. So these are different statistics that is collected during the solving that I would require to extract certain data. So I'm looking at my boundary collision statistics, which would be the impacting on the walls of the pass, and I can gather information like impact, energies, and things like that. Once I've got that, I want to define what I want to use. I'm going to define the intensities that I want to extract. You can add more if necessary. Please note, once these modules have been selected and we have solved our results, we cannot add additional modules because it extracts that data as it's solving. Next thing is we want to define our physics. So on the momentum tab, we want to define our rolling resistance of type C. So because we're using spheres, we want to add additional resistive momentum so that the real particle doesn't really roll like a sphere. So we add that to give it a more realistic results. Materials we can set, obviously on the particles, we can define the density. I'm keeping them as such, but use the densities that you have for your material. Other things that we can edit is the interactions. So for example, particle-particle interactions. We can define the friction coefficients as well as our restitution coefficient. Once we've done that, we're going to import our geometry. So I've defined these STLs beforehand, so I'm going to open them. It then asks me to save the project, which I'm going to do. And then I'll just define what unit I'm going to be in. You can look at the scale here by the geometry limits to get an understanding of if the scale is correct. Yes, so I've got my geometry. I can then create a 3D view to view that geometry. Right now, it is not aligned because we want to manipulate the position by driving its dimensions or positions. So I'm just going to change the coloring of the sidewalls so we can see the inner walls at the moment. I want to refine the top and bottom where the collisions are actually occurring. So I'm going to change the triangle size, which is essentially the pixels. So the finer that is, the more accurate the results will be on that surface. We don't want a fine triangle size throughout because that adds additional computational cost. I'm then going to add a receiving conveyor using the custom templates. So I'm going to add a receiving conveyor, which we can then change the dimensions and the sizes as well as the triangle size if necessary. And we can change the belt profile and also change the belt speed. I'll reiterate on the positioning in a moment. Then we need to add some form of particle. So I'm going to add this particle. I can then define what my sizing would be, and I'm using a default particle material and a sphere shape. I can then add rolling resistance for the sphere to imitate more non-round particles. And then the last things we need to do is define an inlet. So in the inlet, under the geometry, I'm going to create a circular inlet, or with that, I can then go to my inlets, and then I can add a particle inlet. right? And let's define it as the one particle. I can then give it how many tons per hour, and then I can also define the start and stop, and then obviously the entry point is that circular surface I created. The next thing is just defining in the solver settings how long we want it to solve for. Let's say 15 seconds. And then the last thing is define where you want to solve it. So I'm going to use CPU. I'm going to use multiple of 4. I could use GPU, but in this purpose, the particle count is relatively small, so there's no real gains using GPU. Okay, so the next step of the process would be to create my expressions to drive the positions and orientation of my geometry. So I've created a number of here: flow rate, the angle of the bottom, and the angle of the top. The other 3 are really for reference in my calculations. So once I've created that, I can then apply it to certain geometry, which I have done already. So if we have a look at the bottom, I can then look at the wall. I can look at the angles. So I can type in A1. Once I press enter, it will create a expression to reference that variable. So if I were to change that variable, you'll see that it updates there as well, and my geometry updates. Okay, so I applied it to various things, such as the positioning. Let's say look at the top. I'd looked at the positioning. In this regard, I typed in an equation. Um, Once I pressed enter, it will add it to the expression, so you can see the expressions that were used, or the equations. I can then further manipulate these equations if necessary. I then applied it to various things in the project to drive information, or where I want to extract information, and as well driving the actual geometric positions and angles. So the next step would be to solve the project. So I'm going to click solve. This one is already solved, so we can visualize the results. So I'm going to click play. I can then see my particles flowing down. I can change the visualization of that, of the color. So I'm going to change to translational velocity, and I can see how the velocity changes. So it is approximately 30 meters per second when it reaches the bottom. Then the next step would be to create user processes. So I'm going to select the particles. I can then go to the creating a cube. I've set a couple up here. So there's the first cube, there's the second cube for the conveyor, and there's the top cube. I want to ensure the mass flow rate through all those sections is sufficient, or close to that of what the inlet is. Once I've got those set up, I can then look at my curves, curves, and I can see the mass flow going through that. I can compute the statistics if necessary. Then under my expressions and variables, I want to create outputs. I'll drag that across to there and then add that flow rate. So I'm just going to delete that one again, but I've set them up. So what I'm looking at is the average of the mass flow over the last 2 seconds. I did that for the bottom, the conveyor, and the top. Then the next thing would be the actual impact forces or intensities occurring on those regions of interest, the top and the bottom. So if I go to that, I can look at the properties. I can see the impact dissipation. Dissipation giving me an idea of how much energy is lost in the process. So I can then drag that over as well. Yeah, so I've done that for a couple. So if I look at the top, I looked at the sum of all the dissipation on that surface, and I looked at the average of the sum over the last 2 seconds as well. So this is the results that OptiSLang will use to find the optimal based on these specific criteria and things like that. Okay, I have OptiSLang open. I'm going to create an empty project. I'm going to call it untitled. I can give it a name. Let's say demo. I can then go next, and I can finish that. Yep. the next thing is to start a solver wizard. So I'm going to drop the solver. I'm going to choose Ansys Rocky. I'm going to choose the project that I have already done. So let me just go to the OptiSLang. And then let's say I want the latest project. Okay, so then I'm just going to select the output pi and then allow that to open. Okay, so we're going to select, we want to proceed, so we say yes. Okay, it will then delete the project data, but it will then import that project, which you then can update. We'd go to the parametric solver. We can then decide what our references are. So we're not going to be using those, so we can specify those as constants. And then we can also specify our criteria. I'll show you one where that is set up. Once that is done, we can then just say OK. We can then click Run. Okay, so this is the solved parametric system. So let me just to elaborate, I switched those few things off. I then added certain criteria as well. So the criteria I was interested in was the mass flows through the tops. I changed those to constraints and ensured it was larger than my inlet. Just note this is in SI units, so it was kilograms per second rather than tons per hour. I then also added a weighting based on the intensities on the top, the bottom, and on the conveyor. Another objective I was interested in was keeping the loading position and the point of the conveyor as close as vertical as possible. Once that was done, I can then, obviously I need to run it. You can see it succeeded and all these criteria were met. So we can have a look at the different results that it extracted for these particular angles. So the next step would be to do a sensitivity. So I'm going to drag the sensitivity onto that point. It will then ask me a few questions. Again, it will bring information from the previous step as well. So I'm going to say next, and then the criteria were originally defined, but I could add if necessary. Then we can choose what kind of sampling we want. We can use the default, which is fine. If you have start designs that are already solved, you might want to start with those and you can define that. But I'm going to use the default adaptive sampling. Okay, so I then want to finish that, and then it will add the particular information onto the canvas. Right, once I'm there, we can have a look at the various different things. Adaption, obviously, the number of samples can be critical because it determines how long it will solve for. So you can define the maximum number of samples that you want to do. The criteria and all that were brought in from the previous one. And then we can then also look at the design results, but that would then occur when we press solve and it would be automatically generated. So then I would just then go click run. So now that I have the sensitivity data, I can then click on the optimization wizard and select it or drop it on there. So my parameters are going to stay the same as previously, my criteria as well. And then the next step would be defining what optimization techniques I'm going to use. I'm going to use the one-click optimization, and we could also specify the maximum number of design evaluations. I can then select next, and then I can click finish. And then it will create a layout where I can then do my optimization. Okay, so the last step would be obviously to solve the optimization. By clicking that, this is already solved. So if I click on that, I can see the different results that was extracted Obviously, there's a few other ones. There was one failed one, but that was for other reasons. So once we've done that, we can then post-process it. This step, we can post-process, obviously, the sensitivity initially, and we can then post-process the optimization itself. So the first thing I'm going to look at is, for example, the relationship between the two angles and the intensity of the top. And we can have a look at how that changes. We can then look at our various variables, for example, the conveyor, as well as, for example, the bottom. And we can look at the COP matrix, the residuals, as well as the, the COP for that particular model. We can then look at the optimization results, and it shows us our Pareto front, which indicates the optimal solutions. There may be multiple because there's multiple dimensions or inputs that we are changing. We can then look at each design that it's showed us. So I said select the best designs, and we can look at each design and how that is impacted um, on our results. And we can then choose the best design from that. Yeah, so that brings us to the end of the presentation and the demo. I hope you found it useful. Thank you very much.